Hello viewers, in this session we will learn about the singularities, in particular isolated singularities of an analytic function. So, firstly a point in the complex plane where a function f is analytic is called a regular point. So, a singularity is such a point where f is not defined. So, of particular interest are singular points which are surrounded by points which are regular, or in other words, if there is a point A such that in the neighborhood of A f is analytic, then such a point is said to be singularity, isolated singularity of f, and we are interested in predicting the behavior of f and then around this point, or using the behavior of f around this point in order to classify such isolated singularities. So, I will first define a regular point and a singular point. Okay. So, a regular point, we say that A belongs to C is a regular point of a function f if f is analytic at A. Okay, and a point A is called a singularity of A, of f rather, a singularity of f if A is a limit point of regular points. Of f. So, that is a singularity. So, suppose f is analytic, okay, on B prime A r, then we say that f has an isolated singularity at A. Okay, so, the first trivial case is the case where f is actually analytic at A. Okay, so, it's analytic in B prime A r. Recall B prime A r is the deleted neighborhood of A. Okay, so, we are removing A from the ball of radius r around A. Okay, and if f is analytic in this punctured neighborhood or deleted neighborhood, it could happen that actually f is analytic at A. But we did not define it there, that is all. So, in that event we say that such a point is a removable singularity of f at A. Okay. And there are other cases, but first this is first this is the trivial case which we will consider, okay, and then we will classify other kinds of behavior of f around A. So, firstly I will start by giving some examples. Okay. So, consider these functions f1 of z defined by e power z minus 1 divided by z for z belongs to C. Okay. And f2 of z. So, firstly I will complete these three examples, and f2 of z is 1 by z for z belongs to C. One can actually consider f2 of z equals 1 by z power n, n is any integer for z belongs to C. Okay. And f3 of z is equal to e power 1 by z for z belongs to C. I apologize, C minus 0, at 0 this function is not defined. So, C minus 0, and even this is C minus 0. Okay, all these are functions on C minus 0. So, all these have singularities at the point 0. Okay. So, f1, f2, f3 have isolated singularities at 0, at z equals 0. Okay. And we could, f1 could be redefined to be, so these are three different kinds of isolated singularities, as we will see. f1 could be redefined as f1 of z. So, let us redefine f1 as f1 of z is whatever it is given to be, e power z minus 1 by z for z not equal to 0, and let us define it to be 1 for z equals 0. Okay. So, since we know that the limit as z goes to 0 of this quantity e power z minus 1 by z is actually equal to 1. Okay. So, that limit is 1. So, so if we redefine f1 to be 1 at 0, okay, then f1 is actually analytic. One can check f1 is analytic on the whole of the complex plane. So, we have actually in effect removed the singularity at 0 by redefining f1 at 0 itself to be 1, which is the limiting value of the definition of f1 in a neighborhood. So, if the limit, we will see that if the limit of f of a function f in a deleted neighborhood as z goes to that isolated singularity exists, then f will be analytic. Of course, f is analytic in the deleted neighborhood, okay, then f is analytic in the whole of the disk, and that singularity can be removed. Okay. So, such a kind of singularity will be suggestively called as a removable singularity. Okay. So, another way of saying this is the function f, if it can be extended to an analytic function even at the point which is a singularity, then such a kind of singularity is removable. Such a kind of isolated singularity is removable. Okay. So, we will define that in a moment. So, but f1 here has such a kind of singularity. Okay. f2 of z has another kind of singularity. f2 of z, notice that it tends to infinity as z tends to 0. Okay. Whether you consider this definition or that definition of f2 on c minus 0, here also I should have said at c minus 0. Okay. So, so whichever definition we consider, we know that as z tends to 0, the modulus of the denominator becomes larger and larger. So, f2 tends to infinity. And so, this kind of singularity, okay, so this kind of singularity has a definite pattern, f2 of z in modulus tends to infinity, or f2 of z tends to infinity as we call it. Okay. And also notice that z times f2 of z, if you consider the first definition, okay, limit as z goes to 0 of z times f2 of z is 1. Okay. Or if you consider the other definition in the parentheses of f2, then limit as z goes to 0 of z power n times f of z, f2 of z is equal to 1. In either case, the limit of the appropriate power of z minus 0, okay, which is z, times f2 is a non-zero quantity. Okay. And that actually characterizes the kind of singularity of f2 at 0. So, f2 is said to have a pole at the singularity 0. Okay. The singularity 0 of f2 is said to be a pole. Okay. And then we will see something, we will define something called the order of the pole, that integer n here or 1 in this case. We will call that as the order of the pole. We will define that more concretely. okay, and that is another kind of singularity. Finally, F3 you notice has a different kind of singularity. F3 of Z does not tend to infinity as Z tends to 0, okay, and sorry, as Z tends to 0, and F3 of Z does not approach a limit, okay, and F3 of Z does not approach a finite limit L, okay, as Z approaches 0. There is no finite limit for F3, nor does it uniformly go off to infinity. So, it's sort of jumping back and forth. We will see a more concrete pattern to this jumping, and then this kind of singularity is the third kind. We will call this an essential singularity, okay, and we will see that the Casorati-Weierstrass theorem for these kind of singularities. Okay. And in essence, these are the only three kinds of behavior. We will also show that these are the only three kinds of behavior exhibited by a function which is analytic in a deleted neighborhood of a point A. Okay. So, let us proceed to classify the isolated singularities of a function. So, we will start with the removable singularity, like I have said. Okay. So, I will first define a removable singularity. A function f is said to have a removable singularity at a point A if f is analytic in B prime A r for some r positive and if there is a function, there is an analytic function G, okay, on the whole of B A r, which means it is already defined on at the point A itself, okay, with G of Z is equal to f of Z for Z belongs to B prime A r. So, G is an analytic function on B A r which agrees with f of Z at all points in B prime A r. Okay. So, then f is said to have removable singularity. We will give a criteria to identify a removable singularity for a function. So, here is the criteria. So, here is the theorem which states the criteria. So, suppose that f of Z is analytic on B prime of A r, okay, where r is some positive quantity. Okay. There is an analytic function G of Z on B A r, so that G of Z is equal to f of Z for Z belongs to B prime A r if and only if limit as Z goes to A, Z minus A times f of Z is equal to 0. So, if this condition is satisfied, that the limit as Z goes to A of Z minus A f of Z is 0, then there is an analytic extension of f to the whole open disk B A r, if f is already analytic on B prime of A r. Okay. So, and it goes the other way around. Of course, if G matches with f on B prime of A r and G is analytic, then limit Z goes to A, z minus a times f of z will be 0 by continuity of G. Okay. So, so that direction is easy, but the other direction requires some work. Okay. So, in retrospect, this is equivalent to saying that there is an analytic extension of f onto the disk BAR if and only if the limit z goes to a, f of z is defined, if the limit exists. Okay. So, I am saying in retrospect of what we are going to do. So, if we prove this theorem, okay, after we prove this theorem, we will see that will imply that the statement that I have said, that limit z goes to a, f of z, if it exists, then f can be redefined at a in order to make it analytic on the whole disk BAR. Okay. So, that's the theorem. Okay. And in order to prove this theorem, we will first see couple of lemmas. Okay. So, lemma, before we prove this, we will see these lemmas. Let f be analytic on B A prime R or B prime A R, okay, satisfying limit z goes to a, z minus a f of z is equal to 0. Okay. Then integration over gamma f of zeta d zeta is equal to 0 for any simple closed curve. Gamma in B prime of AR. So, gamma should lie in the deleted disk BAR, B prime AR. Okay. Then integration over gamma of f is 0. So, it is a modification to Cauchy's theorem. So, what we are saying is that we can have a point A at which we have a condition limit z goes to a, z minus a, f of z is 0. Okay. And with these kind of exceptional points, the Cauchy's theorem still holds, that the integration around any simple closed curve of f is 0. Okay. If f is analytic in B prime AR. Okay. So, the proof is simple. Okay. So, if the inside of gamma I of gamma, recall we have defined what the inside of a contour gamma is, okay, does not contain A, okay, then the lemma is true automatically by a version of Cauchy's theorem that we proved already. Okay, because then your inside of gamma is completely contained in the domain of analyticity of f. Okay. So, then this lemma is true. Okay. So, if A belongs to inside of gamma, then we need some modification. If A is inside of gamma, then given epsilon greater than 0, we know there is a delta positive, because the limit, the said limit exists of z minus a f of z, okay, and it is equal to 0. Given epsilon greater than 0, there is a delta greater than 0 such that modulus of z minus a times modulus of f of z is strictly less than epsilon by 2 pi. We need this adjustment factor. Okay. So, this is true whenever z belongs to a ball of radius delta around A. Okay. So, then okay. Okay. So, now consider a circle of radius delta 1, okay, with where delta 1 is strictly less than delta 1 is positive strictly less than delta. Okay. So, I will call this circle C delta 1. Okay. Consider a circle C delta 1 of radius delta 1, okay, around A. So, the center of this circle is A, okay, and then integral over gamma f of zeta d zeta, okay, is equal to the integration around this circle now C delta 1 of f of zeta d zeta. Okay. This is because now if you have this contour gamma, okay, oriented in the positive direction, if we take a circle of radius delta 1 around A, okay, then we know by one version of Cauchy's theorem that the integration over gamma of f of zeta d zeta is going to equal integration over the contour C delta 1 of f of zeta d zeta. Okay. So, these are one and the same by version of Cauchy's theorem. Okay. So, this is by Cauchy's theorem, okay, for simple closed curves. Okay. So, then the modulus of this integration f of zeta d zeta is less than or equal to the integration over C delta 1 of the modulus of f of zeta times modulus of d zeta is strictly less than 1 by 2 pi times integration of epsilon, because modulus of f of zeta is less than epsilon by modulus of z minus a f of z is less than epsilon by 2 pi. I have modulus of f of z less than epsilon by modulus of z minus a, in this case zeta minus a times modulus of d zeta. Okay. So, notice this is true for every z in B A delta, okay, and this contour C delta 1 lies completely inside this B A delta. So, for all points on the contour C delta 1, this inequality holds, this estimate in terms of epsilon holds, and so we can say that the modulus of f of z, okay, is less than or equal to, okay, you can say less than or equal to 1 by 2 pi epsilon by modulus zeta minus a mod d zeta, okay, and then divide by 2 pi. Okay, this is on C delta 1. Okay. So, this is equal to epsilon by 2 pi times 2 pi. Okay. So, this integral 1 by mod z minus zeta minus a mod d zeta is 2 pi. So, that cancels and this is equal to epsilon. Okay. So, this is less than epsilon. So, this was a strict inequality, sorry. So, this is a strict inequality here. Okay. So, I get epsilon, this is strictly less than epsilon. Okay. So, so in summary, this integral is equal to this integral and this is arbitrarily small. So, integration over gamma f of zeta d zeta is equal to 0. Okay. So, notice that we have proved this by using a technique similar to Cauchy's theorem, but we are using Cauchy's theorem itself once again. What we are doing is we are considering this contour gamma which contains A in its interior, and we are sort of contracting this this contour to a very small circle around A, and then we are estimating the value of the function f on that circle around A itself. Okay. So, that is a technique very similar to one in Cauchy's theorem, but this condition that the limit z goes to a z minus a f of z is equal to 0 helps us give this estimate, and then we can say that the integral of f around that circle is 0. So, the integration over gamma itself is of f of z is okay. So, that is the proof of this lemma. There are only two cases, that a is in the inside and a is not in the inside of gamma. So, in either case I have showed that the integral is 0. Okay. So, that proves this lemma, and we need one more lemma before we can prove the theorem, but first notice that So, here is a remark on this lemma we just proved. We can have more than one points. Okay. We can have finitely many points. Okay. A1 through an, for which limit z goes to ai, z minus ai times f of z is equal to 0, and of course, with the assumption that f is analytic on on a disk BAR minus the points A1, A2, so on until AN. Even in this general scenario, we can show that we can show that using the very same thing, we can contract these disks A1 through AN, which are finitely many points. We can contract these disks to smaller disks, or contract this region to a very small disks around these points A1 through AN, okay, and then apply this lemma repeatedly to each of these disks to show that the above holds, the same lemma holds with many points having such a condition, limit z goes to ai, z minus ai f of z is equal to 0. Okay. So, okay, even in this case, integration over gamma f of zeta d zeta is equal to 0, where gamma is a simple closed curve in BAR minus E1, E2, so on until the end. Okay. So, we have to slightly modify the technique of the proof of lemma to consider the case where more than one points A1 through AN are inside gamma. What you can do is actually then take very small circles around these points, so that the integration over gamma equals the integration over the smaller circles, which do not contain any other points than one of the AIs inside them. Okay. And then by using Cauchy's theorem, the integration on gamma. Okay. So, maybe a schematic will help. So, here is gamma. Okay. Suppose it contains A1 and A2. You can consider two small circles around A1 and A2, and the integration over gamma will equal the integration on these kind of circles, and then we can use Cauchy's or the limit on the limit condition to show that the integration on these smaller circles of f is 0, and hence the integration on gamma is 0. Okay. So, that is a remark on the theorem. Okay. And we need one more lemma here. So, let f be analytic. What we are going to do is, with the same condition, limit z goes to a, z minus a f of z is equal to 0, we are going to show that the Cauchy's integral formula holds. Okay. So, in B prime a r, and let limit z goes to a, z minus a f of z is equal to 0. Okay. So, if this condition holds, let gamma be a circle of radius r1 less than r. So, I will write this as gamma be a circle of radius r1 with 0 less than r1 less than r, centered at A, then f of z is equal to the integration, okay, 1 by 2 pi I times the integration of f of zeta by zeta minus z d zeta for any z belongs to B prime A R. Note that we use the Cauchy's integral formula to show that f of z is equal to this particular thing, this particular integral on the right hand side, and that was a kind of representation formula for the value of f at points inside this circle. Okay. So, that we have emphasized while showing while showing a version of Cauchy's integral formula. And here this lemma says that that kind of representation formula for f of z, okay, for z inside a circle of radius r1 like this, okay, is still valid if z is not equal to A, z belongs to B prime A r1, okay, provided that this condition limit z goes to A, z minus A f of z equals 0. So, once again we will use this condition to actually show that all the previous results or the Cauchy's integral formula still holds. Okay. So, let z naught belong to B prime A r. So, I am picking an arbitrary point in B prime A r 1, sorry, B prime A r 1, okay, and then I will show that this representation formula holds. Okay. So, consider capital F of z is equal to f of z minus f of z naught by z minus z naught. Then notice that the limit z goes to z naught of capital F of z times z minus z naught. So, firstly capital F is analytic on B prime A r 1, okay, minus the point z naught. Okay. So, we are in a situation like this remark, like in this remark. Okay. So, there are finitely many points and f is analytic in a disk minus some points removed. Okay. So, we are in that kind of situation and f is analytic over there, and limit z goes to z naught f of z times z minus z naught. What is this? This is the limit as z goes to z naught of f of z minus f of z naught. Well, z naught belongs to B prime A r 1 where f is analytic. So, it is continuous at least. So, this limit is 0. Also, for the other ambiguous point A, capital F of z times z minus A, this, what is this? This is the limit as z goes to A of f of z times z minus A by z minus z naught minus f of z naught times z minus A by z minus z naught, and each of these is 0. So, the first one is 0 because of the given condition by the hypothesis, and the second one is 0 because the limit as z goes to A, z minus A is 0. So, all in all this is 0 minus 0, this is 0. Okay. So, the limit exists and this is 0. So, B prime A r 1 minus in B prime A r 1 minus z naught, okay, f capital F is analytic, and at the 2 points z naught and A this kind of condition is satisfied. So, by above lemma, so by the above remark following the lemma, okay, following the proof of the previous lemma, what we can say is that integration over gamma capital F of z dz is 0 for gamma as given. Since we are picking this point z naught inside the circle of radius r1, okay, there is no danger of z naught itself lying on the circle of radius r1, okay, and also a is not on the circle of radius r1 centered at a. So, we have this integral is 0. So, what this means is that the integration over gamma of f of z minus f of z naught by z minus z naught is equal to 0, dz is equal to 0. Okay, so, that is the definition of capital F of z. So, this tells that integration of f of z by z minus z naught dz is equal to over gamma is equal to f of z naught times the integration over gamma of 1 by z minus z naught dz, and we know that integration is 2 pi I. Okay. So, this tells us that f of z naught is equal to 1 by 2 pi I times integration over gamma of f of z by z minus z naught dz, which is what we want. Okay. So, since z naught is arbitrary point inside B prime of A R 1, okay. So, since z naught belongs to B prime A R 1 was arbitrary, okay, the lemma is proved. Okay. So, this representation formula holds for any such z naught. Okay, so, that is the proof of this. Once again, there can be a remark following this, that there can be more points than A itself where this kind of condition can be satisfied, okay, and even then we can have the representation formula where we avoid such points as A. Okay. So, now we are ready to prove the theorem. So, let us go back to the statement of the theorem. So, the theorem says that if we have this really handy condition that z minus a times f of z is equal to 0, okay, in which case the two lemmas following this hold, okay, then there is an analytic extension to f of z at the point A. Okay. So, one direction is pretty easy. Okay. Also, I will slightly add a important term to this theorem. Sorry, I will actually add there is a unique analytic function. So, this function is also unique, which gives more rigidity. Okay. So, this function, such an extension is unique. Well, the uniqueness is immediate because G and F agree on a set with a limit point. So, so by the identity theorem, the uniqueness automatically follows. Okay. So, that is not much of a punch, but nevertheless uniqueness follows. Okay. So, proof of theorem. Okay. So, well, the necessity condition is easy, one direction of it is easy. Necessity says that well, requires that G is continuous. So, which implies that limit z goes to a z minus a f of z, okay, is equal to limit z goes to a, there is a unique extension to f and that is G. Okay. So, we are assuming that. So, then this is z minus a times G of z, f is equal to G, and then this is equal to limit z goes to a. Well, I mean this is 0 and that is 0. So, this is equal to 0. Okay. So, the necessity is really easy, uniqueness follows from of G follows from the identity theorem. Okay. So, let me be more clear here. What I mean is, if we know that there is a function G which extends f to the point A as well, then it has to be unique by the identity theorem, okay, because f and g have to agree, that is the condition on G. Okay. So, f and g have to agree on B prime A R. which is a set with limit point. All right. So, now I have to assume the condition that limit z goes to a, z minus f of z exists, and I have to show that f function exists. Okay. So, now suppose limit z goes to a, z minus a f of z exists, or is equal to 0 rather. F of z is equal to 1 by 2 pi I, okay, integration over C r 1, okay, of f of zeta by zeta minus z dz, okay, where C r 1 is a circle of radius r 1 centered at a with 0 strictly less than r 1 strictly less than r, okay, and z not equal to a, okay, z belongs to b prime a r, b prime a r 1. Okay. So, by considering large enough circle, we can actually include all the points in b prime a r. Okay. So, this actually suggests the definition of the new function g. Okay. So, g of z, so define g of z is equal to, well, we are forced to define it to be f of z for z belongs to b prime a r, okay, and define this to be 1 by 2 pi I integration over C r 1 if you please of f of zeta by zeta minus a d zeta. I apologize, this should be d zeta, okay, zeta d zeta for z equals a. Okay, so, we will force it to be equal to this representation formula, g to be equal to this representation formula when z is equal to a. Okay, we will show that g is analytic. Okay. So, the limit as z, or yeah, we can say limit as h goes to 0 of g of a plus h minus g of a by h. There is no doubt that g is analytic in b prime a r because f is. Okay. So, we will calculate this limit. This is equal to 1 by h times 1 by 2 pi I times the integration over C r 1 of f of zeta by zeta minus a plus h d zeta minus 1 by 2 pi I times integration over C r 1 of f of zeta by zeta minus a d zeta. This is equal to 1 by h times 1 by 2 pi I times integration over C r 1 of f of zeta. I will combine these terms, okay, I will clear the denominator, I will get zeta minus a minus zeta minus a plus h. So, that will give me an h in the numerator divided by zeta minus a plus h times zeta minus a. So, these h's cancel and I have this is equal to 1 by 2 pi I. So, I have a limit hanging in there, limit h goes to 0, limit h goes to 0, etc. This is limit as h goes to 0 of 1 by 2 pi I integral over C r 1 f of zeta d zeta by zeta minus a plus h times zeta minus a d zeta. So, now I can take the limit into the integral, okay, and then this is equal to 1 by 2 pi I integral over C r 1 of f of zeta d zeta divided by zeta minus a squared d zeta. So, this limit exists, limit h goes to 0, g of a plus h minus g of a by h, it exists and it equals 1 by 2 pi I C r 1 integration over C r 1 of f of zeta d zeta by zeta minus a squared d zeta, whatever that value is. Okay. So, g is analytic at a and g is a extension of f as desired. Okay. So, that completes the proof of this theorem, and we will see other kinds of singularities next time.